Okay, hello everyone. My name is Verian, and I'm grateful for the opportunity to give the presentation here. So I'm working with Laticrete International. We are a construction materials company. So in this presentation, we will discuss about 3D printing in construction area and why this technology has been gaining its popularity in recent years. I will also present several types of 3D construction printers, which are usually have a larger printing volume as compared to those desktop 3D printers. In this session, we will also talk about the design aspect and for formulating 3D printing material, some of the test results, and a brief process of scaling it up from lab scale to construction. So what is 3D printing? 3D printing is a method of building an object through a 3D computer model by using 3D printer. So in simply put here, so first we generate the model using computer by any 3D software, and then slice the model by using slicing software. By slicing the model, we will have the G-code, which will serve as the input for the delivery system. The delivery system usually consists of a 3D printer, a mixer, and a pump. So the materials is mixed in the mixer and then pumped through the hose, usually, to the end, to the extruder tip, which is basically the tip of the 3D printer. As the result is the 3D printed structure, which is obviously similar to that of the 3D model itself. And all of this process is controlled simply by using a computer. So why this technology has been gaining its popularity? It's because it is more efficient than the conventional construction method. So it requires less manpower, which resulted in a safer working environment because not so many people are needed in the job site. And also it enables us to do the construction faster because most of the work are done by using 3D printer. 3D printing also enables us to be more sustainable because by printing the structure, we can be more efficient in designing the structure. For example, here on the left is the precasted stairs as compared to the 3D printing stairs. So in some part of the structure can be left hollow when it is 3D printed without compromising its structural integrity, meaning that we use less materials and no formwork is needed for a 3D printing method. In several studies, it's been reported that the cost of the formwork can contribute to 30% to 60% of the total material cost in a project. Moreover, 3D printing method enable us to print more complex structure. For example, here is a spiraling tower, which is rotate 5 degrees per layer, and it's built just within 5 minutes. Compared to the conventional method, usually we may need to build the mold or the formwork and then cast the specimens. So this method is more efficient and faster. Another example is the 3D printed concrete pavilion as presented in the picture here, in which each panel is 3D printed and each panel is unique. Another example here, you can see the curve. So comparing to the conventional method, we either need a very well-trained labor to create a curved wall, or we need to use formwork. But with 3D printing, we can just print it without the need for formwork, and also the printer will do the work. So this 3D printing possesses so many potentials, which the efficiency that it provides. With the benefit, its potential can be the solution to provide affordable house for community across the globe. For example, currently the project by New Story and Icon in New Mexico and 3D printing restroom project in India is still ongoing. The 3D printed structure also potentially more resistant towards fire, as we can design the material accordingly. An example to be resistant towards fires. This can address the fire hazard problem in the areas which are prone to wildfire. As we know that recently some of the areas like California and Australia were hit by the wildfire, which burned down many houses, leaving many families losing their houses. 3D printing also can be used to build temporary shelter for refugees at the area hit by the disasters. So in military, the 3D construction printing can be applied in building barracks. So if you can see here on the right picture, the printed structure has a certain geometry which is designed accordingly so that it can be more resistant to blasts. So 3D printing, it's part of the future for construction. In the future, robotic 3D printing has the potential to be used in building human settlement on the other places outside Earth. So for those of you who are familiar with Star Trek, so probably we will find in the future we won't send Captain Kirk and his Starfleet crew to explore the space, but instead we might find ourselves sending robots to explore and build some settlement on the other celestial bodies. So there are several types of 3D printers available out there. In this case is construction 3D printer. The first one is robotic arm. The robotic arm usually has 5 to 6 rotational axes, which enable the printer to print not only in horizontal plane, but also a diagonal plane. The second one is the gantry system, usually consists of several columns and beams, in which the printer head is mounted in one of the beams. This printer is usually huge and require an accurate alignment for each components of the frames. Another one is Delta 3D printer, in which the printer head or the extruder is held by 3 arms. Each arm can be moved up and down independently. The fourth one is the crane type. So for the crane type, usually the printer has a tower which support the cantilever arm. The height of the tower itself can be adjusted, and also the cantilever arm, the length of the cantilever arm can be extended to increase the printing volume. At the end of the cantilever arm is usually where the extruder mounted. The fifth one is known as the SkyBAM. So the SkyBAM, also known as the Big Area Additive Manufacturing, this 3D printer is developed by Oak Ridge National Lab. The SkyBAM has the printer head mounted by wires. One wire is controlling the vertical movement, while the other 4 in this picture are synced to move around the printer head around the printing area. So the same principle being used here for SkyCam. So in Laticrete, We design our materials to assure that we only produce best quality materials. Our 3D mortar are designed to be printable, easy to use, and adapt to various types of 3D printers, pumps, and environment. Moreover, we can design our material accordingly to the place and with different level of strength to meet the requirements for specific project. We design also materials to be durable. So we pass the freeze-thaw test ASTM C666 with durability factor is above 95% after 300 freeze-thaw cycles. And our design also being innovative, in which we can design with different weights, colors, textures. And of course, our products are cost competitive while maintaining its quality. So in the lab, we start our work first by gathering information through reading papers, attending lectures, watching videos, conference, and so on. So after gathering the information, we design our own formula in the lab. After designing the formula, we tested the formula by conducting several lab tests, including the fresh properties and also the printability, in which we did a small print in a lab scale using a modified desktop 3D printer. Furthermore, we also assess the mechanical properties of our materials, which include compressive strength, tensile, flexural strength. For the durability aspect, we conducted the permeability test, rapid chloride permeability, which is ASTM 1202, which indicated that our materials tend to have a low permeability, the shrinkage, and also the freeze-thaw test. So it has been reported that one of the challenges in this technology is the lack of bonding adhesion in the printed layers. So we evaluate the adhesion test by having a cold joint specimens and non-cold joint specimens. And for non-cold joint specimens, so we tested the non-cold joint and cold joint. For cold joint, the specimens are treated with adhesive and non-treated. The cold joint is a plane of weakness in concrete caused by an interruption of delay in the printing. It occurs when the first batch of concrete has begun to set before the next batch is printed on the top of the first batch, so that the two batches do not intermix. The sample here can be seen that we printed specimens and then we cut the specimens. We printed the lower part on the first day, and then the next day we printed the upper part, this leaving the layer between the lower part and the upper part become the cold joint. So we either treated the cold joint by applying adhesive before we printed the second part, or we leave it untreated. And we also do non-cold joint tests, which means that we directly print the lower part and the upper part in one print. The results indicated that, we also apply epoxy at the end of the specimens to improve the grip, because the test method that we conducted here is basically a direct tensile test. So the results indicated that, the bonding improved along the edge of the specimens. And we tested the normal weight specimens and lightweight specimens. It appears that the lightweight specimens have higher interlayer strength. the application of adhesive or treating the cold joint is also proven to be effective by reducing the probability for the failure to occur at the cold joint from 92% to only 8%, and also from 100% to 0% for the lightweight material. So this means that indeed, when the cold joints are not treated, most of the failures occur at the cold joint. However, the cold joint can be improved, the bonding there can be improved by applying a thin adhesive on the surface before printing the second part here. So in addition to assessing the tensile adhesion of the cold joint, we also experimented with cure on demand, in which that we try to inject accelerant just before the material being extruded. So in this picture, you can see that there is a mortar channel because we developed mortar, the 3D printable mortar. And then we inject accelerant, and then the accelerant and the mortar are mixed in this static mixer. As the result, when being extruded, the material will cure faster. The benefits of this method is that we can use a low viscous mortar here, so that the probability, the risk for having clogging in the pump is lower because we use less viscous material. We also have the more control, and by accelerating the curing of the material means that we can do the print faster. It can be seen here in the picture. When we don't apply the cure on demand, but just use less viscous material, the deformation of the specimens seems to be significant as compared to when we use the same material with the same viscosity and we inject accelerant. The integrity, the deformation seems to be significantly less than its counterpart. However, these technologies, obviously, it becomes more complex because the need of controlling the accelerant, the dosage, and the printing, and so on, and also it comes with a price. And having it intermix here is not easy. Some static mixer might be not sufficient for us to have the mix to be homogeneous. So from the lab, we conducted several field trials. Obviously, in the field trial, the scales are larger than the lab. So we conducted in the North America here with a company called Crane in Virginia, and also another Crane. The Crane, we used gantry type 3D printer. And here in the middle here is the test print with 20 Additive Manufacturing in British Columbia. They also use gantry type 3D printer. On the bottom left is the field trial conducted at the Ball State University using a robotic arm 3D printer. We also did some tests in Europe to test our materials. So our materials have been tested by various companies by using different types of 3D printer. And in the Middle East, we conducted the test using a gantry type 3D printer as well. And these materials are developed locally using local materials in Dubai. Similar case in India, we develop our formula locally by using local raw materials. And yeah, we did some test print. From the field trials, we further our work to the printing project. The first one is the DE Stress 3D Concrete Pavilion. This 3D printing concrete pavilion is designed by Dr. Battaglia from Ball State University, in which each panel is unique and is printed by using our material. And once all the panels is put together, the structure will hold its shape together. This has been a part of Columbus exhibit last year from August to December in Indiana. The second project that we have done is a 3D printed house in Dubai. Can be seen here. So for the house, so the walls and the parapets of the house were printed. For the walls, it took about 90 hours printing time for printing all the walls. And for the parapet itself, it took 40 hours printing time. So compared to a conventional method, this method for printing the walls and also the parapet probably took less than, probably around 6 days, less than 6 days working hours. I mean, if the printer is working continuously. In reality, obviously, we take some rest in between. So let's say that in one day we only print for 8 hours. The next day only print 6 hours and so on. But along the way, indeed, there are many adjustments and also many challenges due to the technical issues, the pump, the weather, and so on. So in summary, there are still many benefits, potential that we can dig up from this technology. This technology can provide us to improve our sustainability in construction, safer, more efficient, and faster. Also, it enables us to innovate more in terms of the shape, structure, and many others. One of the challenges for the cold joint, it can be mitigated by applying adhesive. But also, I believe there are many other ways in improving the cold joint, either by applying reinforcement or also by changing the shape of the printing surface. So by having, let's say, a zigzag surface, which will improve the surface, which will increase the surface area, obviously have the potential to be better than having only printing flat area. So there are still plenty of room in innovation in this 3D construction printing area. From the materials still need to be improved, so be more durable, easy to use, robust enough so that it can accommodate many types of 3D printers. And also the delivery system, the robot, how can print more efficiently, more accurately, more durable, because we face some problems with the pump. The pump sometimes couldn't deliver constant feed for the materials and water and so on. And also there are still many improvements can be done in terms of the software, the computer. So there are no specific standardized tests and code for this application yet. So currently also in the future, I believe we will come into consensus in developing the test method and standard for the 3D printing application. I think and these are the reference, and yeah, I'm open for any questions, and thank you so much.
Okay, we have multiple questions here. What type of additive was applied to the cold joint specimens during the direct tensile test?
Oh, what type of additives? The adhesives, okay. Then we use one of our products called 254 adhesives. So it's commercially available adhesive. So this adhesive usually used for tile installation.
Okay, thank you.
Yeah.
Another question is, how effective are 3D printed structures? I guess how resistant are 3D printed structures in earthquakes?
In earthquakes, yes. To answer that question, actually, we still don't know yet at the moment, and the research itself is still ongoing. I believe some 3D printing company and universities are still conducting this. And we also currently in collaboration with 3D printing company, which can print large scale specimens for this kind of test. So the answer is we still don't know where the potential is there, and we are still working on it.
Okay. Did you find any difference in mechanical strength for concrete printed with the accelerator?
The answer is yes, especially in the development of early strength. But indeed, in the long term, it can affect and also it cannot. It depends on the type of your accelerant, the compatibility, and the dosage that you apply to your mixture.
Okay. So I guess the question is slightly reformulated. How do 3D printed structures resist tensile stresses?
How 3D printed structure resist tensile stresses? So in structure, in let's say the house that we printed, we work with structural engineer, and somehow we come up in a method on how to apply certain reinforcement rebars in the structure. So in addition to the material design itself to have a certain tensile strength or flexural and also flexural strength, to resist tensile and flexural strength, it will also depend on the structural design. With sometimes it can incorporate some rebars. So both materials and the structural design.
Okay, great. And the last question is, how do you ensure water tightness in 3D printed concrete structures?
How to water tightness?
Yes.
Which, if I'm correct, is it permeability?
Resistance to, yes.
Oh, okay. Yeah. So in many cases, well, one thing, the material itself we designed to have low permeable. It has, according to ASTM C1202 rapid chloride permeability test, our material has a low permeability. That's one thing. The second thing is that we have tested our printed materials, even though it depends on the printed surface, on how rough, how smooth, but we can apply additional coating, water membrane, and so on. The third is how thick will you print it? Let's say 2 inches wall will be more permeable than if you print 4 inches thick wall. So there are still many improvement can be done, many work can be done in this to improve the water tightness in addition to designing the material itself.